So next up, we have a talk from Ethan Schreyer, who's going to tell us about gas donated by the extreme mass loss of planets. Take it away.
Hi, everyone. It's a pleasure to be here. And Jess outed me to going to karaoke last night, so hopefully I don't embarrass myself. Yeah. So today I'm going to try and convince you that circumstellar gas generated by the extreme mass loss of planets is both interesting and detectable. So we're going to change tack quickly, and I've put a plot up of something seemingly unrelated. It's a plot of the log RHK of a sample of field stars, main sequence, and hot Jupiter hosts. And for people who don't study stellar activity, log RHK is essentially a measure of the activity of the star got from observations of the calcium 2 H and K lines. And what you may notice by eye in this plot is that the hot Jupiter hosts tend to have a lower activity than the main sequence sample in general. And this is statistically significant. And so the question is, why is this happening? So the kind of boring answer is selection effects. And the authors of this paper do mention these, and they do try and do some correction, but maybe there are other selection effects going on that haven't been accounted for. A slightly more interesting physical explanation is, can close-in giant planets inhibit the magnetic activity of stars? It's a cool explanation, but I don't think there's any physical models which actually can produce this yet. And a third potential possibility is that extreme mass loss from planets can lead to circumstellar gas obscuring the star and blocking the calcium 2 H and K line. So the star's activity is not actually less, it's just what we observe. And this idea was inspired by observations of this system, the most extreme system in this sample, WASP-12. And WASP-12 is indeed a very extreme system. It hosts a giant planet on a one-day orbit, which is about 3 stellar radii, so incredibly close. And people have, because this planet is so close, it's thought to undergo intense atmospheric escape, and so people observe this planet. And these observations are particularly interesting because they're not taken during the transit of the planet. And so what I'm showing is the magnesium 2 H and K lines and the calcium K line of WASP-12, which are in both these plots in the black, compared to other stars of similar age and rotational period. And the line cores where the chromospheric magnesium and calcium emission is coming from are completely depleted. And so this, it could just be an incredibly inactive star, way more inactive than the sun, which is a bit strange because people think the sun is at the kind of bottom level of activity, or potentially there's this gas which is blocking the cores of these lines. And so Jess introduced this nicely, but is this kind of a physical explanation? Does it make sense physically? And these are pretty cool 3D simulations of escape done by Morgan McLeod. And from left to right is increasing stellar wind strength. And you can think about this as, from right to left, increasing planetary mass loss rate for the same stellar wind. As Jess highlighted well, really what determines the geometry of this is the ratio of the stellar wind strength to the mass loss of the planet. And if the mass loss is very strong, then the stellar wind can't push the gas from the planet out, and it forms a ring around the star. And if you think, oh, magnetic fields, the gas can be strong enough, like the gas pressure or the ram pressure of the gas can be stronger than the magnetic pressure of the star. So it doesn't necessarily just accrete onto the star through kind of accretion funnels. So if there is this significant amount of circumstellar gas, surely it should be observable not just in calcium, which is not thought to be a big escaping gas, but something like helium. And if you ask any person who does atmospheric escape, the helium line is a great line because it's our most productive in finding escaping planets so far. So Daniel gave a great introduction to the helium line, so I won't talk about it much, but on the right is a plot from James Kirk, which shows a whole bunch of observations. So this line is pretty well used. But it's not that easy to detect a circumstellar gas disk because unlike a planet, you can't detect it via temporal variations in the observed star, right? A planet, you know it's transiting, so you can tell that the helium line, or you can look at the helium line during the transit. Whereas for a circumstellar gas disk, it's just there the whole time. So you need to be a bit more subtle about how you detect it. And it's not always obvious, if you look at the stellar line, what comes from the star, what comes from the disk. And to really detect these, we need to understand the stellar lines very well and understand the properties of the stellar lines. So here I talk about using complementary observations of the helium lines of stars and the log RHK to diagnose these disks. So here is a plot from Smith of how the helium equivalence width of a star scales with the log RHK. And as you can imagine, they're correlated. They're both chromospheric lines. And so stars generally move along this track based on their activity. Okay. And here are kind of schematics of what the stellar lines are. And now let's see if I add a disk around the star and do that observation in helium, and the disk absorbs helium, then the line gets deeper. And we can imagine that it will move off this track. Now imagine that the disk also absorbs in calcium, and the star log RHK becomes kind of what we observe as more inactive, and that moves. So the star now moves off this kind of activity track. So this is good. This means that by looking at both these lines, we should be able to distinguish what's kind of natural activity of the star to a star hosting a disk. And to kind of do this more quantitatively, I made some models of the circumstellar gas disk, and this is about the simplest model you can make. So there's a whole bunch of assumptions which you may or may not like, but it really doesn't matter that much because no matter what assumptions you make, if there's a whole bunch of gas there, it'll be hard to get it not to absorb in helium. And so I took the field star sample from Smith and put a disk around it and looked at the properties in helium. I didn't actually do any absorption in calcium for this plot, but it doesn't really make a huge amount of difference to the results. But what you can see is now that the population lies pretty far off the field stars. So if we observe these hot Jupiter stars with both calcium and helium, we expect that if the circumstellar disks are the reason for these low log RHK, then this plot shows that the population should look different in this plane. Okay, so what about the transit? There's a planet there, and how does the circumstellar gas affect the transit? And it really acts like a giant spot, so I don't know if that makes star people happy or not. But what you see here is if I plot the transit with and without the circumstellar gas, you get different depth. And this will affect inferences made about the transit and also potentially make the transit just unobservable. So you can imagine if the disk is optically thick enough, this red line, which is the transit with the gas, will move up to where the optical transit is. And you can imagine it also affects the spectrum. So the blue line here is a planet at mid-transit with escaping helium. observed with no circumstellar gas, and it's your classic helium absorption line. And as you add circumstellar gas, this absorption line disappears. And you get all these funny wiggles, which would probably look like noise. Moving the planet and the gas leads to a bunch of interesting looking transits. So potentially, this is a way to kind of understand where this disk is, if it does exist. And I finished a bit early, but here's a summary. Pretty much, stars hosting close-to giant planets appear to exhibit low activity. And I think complementary observations of the calcium and helium lines can indicate whether this low activity is due to the star hosting circumstellar gas. And so I'd encourage any observers who have the opportunity to look in the helium lines to just shoot a bunch of observations at stars. You won't need to look at them for very long. And it doesn't need to be doing transit, so it's very easy to schedule. The presence of circumstellar gas will pollute a transmission spectrum. And kind of as a final note, if these things are detected, they'll be able to tell us lots about the mass loss and evolution of hot Jupiters. So Jess mentioned how most hot Jupiters aren't thought to lose enough gas to change their properties. But for a very small subsample, exactly the ones that are thought to maybe produce these disks, the extreme mass loss generated by something like Roche lobe overflow could make them lose their atmospheres completely. And if these exist, or if they don't exist, that's also telling us a lot about the properties of stellar winds. We can put limits on what the stellar wind of a star is based on whether the gas is pushed away or it's there. Okay, so yeah, that's it. Thank you.
Thank you, Ethan. Questions? Let's go.
Can't see anything.
There it is.
Just a comment and a question. So our prime HK is an extraordinarily blunt tool. As somebody who's written papers on R prime HK, it's not that much better than photometry. So we're taking a very metal-rich sample, right? Hot Jupiters are very biased metal-rich, and we're applying a line from 40 years ago for a solar population averaged calibration sample. So you're looking at a very metal-rich star that's also lower log G. And I'm just worried that that's biasing the sample. So the entire beginning of the premise that the HK is somehow biased, we're missing the young ones. We're missing young metal-rich stars. They're not near us in the galaxy. So there's no surprise that there aren't extremely young ones. But the older ones are probably these are metal-rich older stars. And the opposite side of that is we see metal-poor stars in the solar neighborhood that look chromospherically more active than you'd expect for their age. So I guess the question is, what's the other evidence for the circumstellar gas? Do you see anything in other lines like H alpha, any of the Balmer lines? Is there something to fix on that? Because as soon as you say there's like clumps and clumps of circumstellar gas, and it's somehow supported by some bias in H and K, which I think is too blunt of a tool. Just what's the other evidence? This is beyond the UV absorption. Sometimes we see it, but I mean like really like a lot of circumstellar gas.
Yeah, so I completely agree with you, and I am worried about those biases and essentially working on trying to figure out if a better job of comparing these samples can be done. For evidence of circumstellar gas, as you know, it's difficult because it's hot, so pretty much all the absorption lines are in the UV, and H alpha is, again, a difficult line to look at because the way it's populated, you don't expect that much H alpha to be there. So I think that, yeah, there's completely the possibility that circumstellar gas disks don't exist. From a physical standpoint, there's no reason why, with extreme mass loss, you shouldn't have circumstellar gas. So I guess probably the best thing would be, if it's possible, and I don't know, you kind of sound like maybe it's not, to do a better job of calibrating the log RHK sample comparing hot Jupiters and field stars. But yeah, that's kind of my impression of that, yeah.
Thanks. Okay, we're going to have to wrap up there. I saw there were loads of questions, so come and find Ethan during the break. But let's thank Ethan again. And then